Yeah. So the more electronegative is, the more
Oh yeah, surveillance structures, they're not strong enough to pass electrons, but ionic structures are. It says here that covalent structures aren't strong enough to connect electrons, that's why they like share the atomic, atom. And then ionic structures are strong enough to pass
Not this.
don't do that. They really said they were hard and I read about it, but I didn't see it. It just like, I don't remember that it would be bond so you have because those things they're yeah, and then it's just another very valence with the healthy cell one wants those hydrogen or just oxygen and the dawn. Because it was like oxygen and then we got and then kind of weird because it goes not I think it's hard to remember it.
All right, pause your conversations in 10 seconds, please. All right, I'm going to ask for a couple groups to share out, and I'll add to this. This is a really good discussion piece. This is like the majority of the background for today. Then we're actually going to draw the Lewis structures, which is what the last question was. And some of you guys actually had some in your pictures already, so you're actually at a really good jump start already. So, why do atoms bond? I want like a really, really concise answer, okay? Really concise answer. Chloe's group.
We just said to become stable.
Okay, so to fill valence shell. I'm going to put valence electron, like VE, like that, shell. Can I get something added to that? Lindsay's group right here. Basically the same thing. Does anyone have anything else to add to that? That's it. That is really it. They have stable octet, right? Look, can we go ahead and put octet right here? And that octet is the same as a noble gas. Gas electron configuration. Most of the time they get octet. There are exceptions to that rule as well. But because their valence shell is filled, that means they're stable. How can they do that? They can either do it by donating an electron or sharing an electron. That's about it. That's what ionic and covalent bonding is. Well, oh, how does electronegativity play into this? How does electronegativity trend, by the way? Like this, right? Okay. So, who is the most my board is so off. Okay. Who's the most electronegative element? Good. I heard mostly fluorine, right? Because I know some people are going helium, neon, argon. Do they really want electrons? They are happy as can be, right? They have octet, or their helium's small enough it doesn't have octet. It's duet has 2, but everything else does 1 octet. So fluorine would be the most electronegative. And that's going to be because it needs 1 more, and it's small, and its nucleus is really close to its outside, so it does play into the PR trends quite a bit. What are the differences in shapes? So this group up here, start me off.
The ionic forms a lattice structure.
Right, so covalent things for molecules. They look different than lattice structures. Lattice structures have layers and 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 layers of ions, 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 ions. Molecules are just like, all right, here's a water molecule, H2O. There we go, just one little molecule like this. Whereas a lattice structure has layers and layers and layers. So the structures do look very different. So give yourself a description there. The difference is in strength. Which one's the strongest type of bond? I think this group right here, McKinley's group. Ionic or covalent? Say again? Ionic. Can you tell me why ionic is the strongest?
They're charged opposite to one another, so half of them they're all kind of attracted to each other.
Right,
So
and they're
since they're alternating between one another.
yeah,
their
like
neighbors pull them together.
I'm not sure if you guys can see that, which is talking about this gray one in the middle. It is attracted by all the green ones around it, and then all the green ones around it, that's where all the green ones it. Blah 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 blah. It keeps going, going, going. So this lattice structure, I'll pass this around and you can see it. This lattice structure is a good representation of how ionic bonds are strong because the opposites attract times like 6. There's like 6 ions around it. So it's very, very, very strong because of all the attractions. And there's a word we use for that. It's called electro. Can anybody fill that out? Electroblank attraction. Static attraction. So we're just talking about the fact that that's very, very, the opposites attract, the full-on positives and negatives attract more so than just the shared bonds that are between. They're just not as strongly attracted. So I can break a covalent bond a little easier than I can break an ionic bond. All right, special traits. Can I get a special trait from Robbie's group?
Ionics are they only conduct electricity when they're plugged in.
Okay, so special characteristics or conditions to their conductivity. Okay, so I'm just going to say that loud. This group.
Bonds dissolve easily in any polar solvent.
Ooh, I like that. Polar solvents. And that's that polar word. Do you know what that means? Not similar, but not specific. Miles? What's polar mean? Yes. Okay, so I'm going to draw that out for us. So polar solvent, example of polar solvent is water. All right, we're going to learn how to draw this today in a second, okay? So I'm going to tell you right now, this is water. This side up here is partially negative, and this side down here is partially positive and partially positive. So you just said different charges on different sides. Do you see different charges on different sides? Yeah? What's the North Pole have here? A negative charge on, oh my gosh. A negative charge kind of on the top up here, and then a partially positive charge on the bottom. So that's what polar is, and we are going to get into that actually a bit more tomorrow. But it seems like some people have some background knowledge on that. It's great. Okay, that's pretty good right now. There's one more trait I need to talk about for our covalent. Did anybody see the word volatile? Write down volatile under your covalent someplace. And then raise your hand if you wore deodorant today. Yeah, pretty sure. If you are wearing deodorant today, everybody raise your hand. All right, so right now, your hand is raised. Thank the Lord we're in deodorant, right? So we have this nice aroma coming off of our underarms, hopefully. And that's just because the deodorant has scent particles in there, and your body heat warms up those scent particles just enough to make you smell nice. That's how deodorant works, that's how air fresheners work, that's how, oh gosh, perfume, cologne, body wash, shampoo, anything that smells good is because they have covalent molecules in them, and when your body warms it up just a little bit, they start to evaporate off your body. So volatile means easily vaporized. And as the scents get, or the molecules get vaporized, they come to your nose, and then you smell them, which just makes you smell nice. Thank the Lord for chemistry. All right, questions on this right now? Yeah.
Just like perfume, but like we can like already smell it even when it's in the bottle and it's not really like.
It's because that is so volatile, it doesn't even require body heat. Deodorant, I mean, a lot of things that you can smell, but it's because they start to vaporize probably at room temperature or even lower, but then it really exasperates it when we add a little body heat to it. Yeah, because you're vaporizing it faster. And then it doesn't smell good anymore after it's all vaporized. Okay, so that's a pretty good synopsis. Let's talk about Lewis dot models now. So who even knows what Lewis dot model is? What is it, EJ? Okay, so it's a way to show the valence electrons as what? As dots, right? So if I'm an ionic bond, what do I do with my valence electrons? Say again? I give them away, and I have to draw that in a picture. So here's what we're going to do. We're going to draw that as a picture right here. All right, so I'm going to go to my picture first, and I'll come back up here. You're going to label this ionic dot models, or Lewis dot models for ionic compounds, however you want to label it. So if I have sodium, you guys have a periodic table out? We are drawing some images, and then you might want to put them in your notes. Does everybody have a periodic table out? You should. You should. Okay, so everybody find sodium. Point to it. Tell me what group it's in. Group 1, how many valence electrons does group 1 have? 1. Everything in group 1 has 1 valence electron. You see 1 dot. Everybody find chlorine. Chlorine's in group 7. How many valence electrons does group 7 have? 7. It's really easy. If you can tell like the group number, you can tell the valence number. So if I'm drawing sodium, I'm going to draw it with 1 dot. Go ahead and draw sodium with 1 dot. Like this. And we are going to allow sodium, which is a metal, right? We're going to allow it to get rid of its valence electron. Why is it trying to get rid of its valence electron? Nick. So it can back up to its last 8, to its last noble gas electron configuration or octet. So chlorine being a nonmetal is already really close to octet, right? It needs to gain 1. Well, it doesn't just steal it from anybody. It's probably going to take it from a metal. Likely take it from a metal. Sodium's valence electron gets transferred, and the transfer is represented by drawing an arrow. So it's not like, oh, I'm sharing. I know you're saying, oh, I'm sharing, but if I give Miles a cookie, it's no longer mine, right? He's not going to like, here, I'll break it in half, you can have the other half. That would be a covalent bond, right? He's like, no, I'm going to go ahead and eat this, I'm going to break this. So that's taking it, that's being donated, that's, you know, he has it, I no longer have it. So that's the donation process. You're drawing this arrow. Now, sodium, you can see here has a what charge? 1 positive, right? And I know the 1's not there, but you can write the one for yourself. So that's not 11, that's a 1, by the way. My marker is really off. So our sodium ion has a 1+ charge because it lost 1 electron. And then to make sure it's very clear that chlorine has octet, you do put brackets around it, and you can see that right here, as well as the 1 negative charge that the chlorine now has, because it has an extra electron. Yeah.
So this could confuse me actually, but if there's just a plus and a number beside it, it's just 1.
Yes. So if it's just a plus with no number, it's assumed to be a 1. Right. Okay, but overall, this entire ionic compound has a 1+ and a 1 negative. What's that make together? 0, or neutral. So know that all ionic compounds, after they have bonded, I know there's 1 with a positive and 1 with a negative. You know, maybe it's a 2 positive and 2 negative. Still, overall, they're neutral. Does that make sense? Okay, so moving on. Let's go ahead and you guys do one for magnesium oxide, MgO. go ahead and draw out your structure just like we have here for MgO, and ask people at your table if you need a little help. I'm just going to do one or two examples of each. That way you have an idea for your homework tonight what you're going to do. So Emily, what's the first thing you did?
I did what you do, and I had 2 valence.
Because it's in group 2, so 2 valence electrons. Okay. Kayla, what's the next thing?
Draw oxygen with 6 valence.
And I just had a good question about that. I'm going to draw them all in pairs. Electrons like to be paired up. Remember, like in their orbitals, they're paired up a lot of times. So trying to draw them in pairs. That's okay if you didn't. And then let's go. Kim, what's next? And they do what? So they're getting donated to oxygen, right? Okay. And then Kyle, what's next?
You're gonna write Mg and then -2 or -2
To what?
or 2 to minus or
I know. So this is the weird thing. As they lose electrons, we're like, oh, that's bad. That's
oh no 2
negative.
plus 1.
But they lost 2 negative charges. They lose electrons to make them overall positive, and
Then put brackets
brackets,
and then put oxygen with all 8.
and 2 minus. You see where our pen is, and it's like weird here. Yeah.
So why wouldn't we put brackets around
So you can put brackets around magnesium, but there's nothing to bracket. The reason I'm putting brackets here is because I want to show that this bracket contains all the electrons, and now all those electrons are on oxygen. It's just to say these are mine. That's just brackets around them. Yeah.
For the actual that structure of oxygen,
Yeah.
would you like fill up the whole thing so that it would have 1 on each side? So it's filled.
Truly, and that's a bit more advanced, but truly it's 2s, so 2 of them get filled first, and then 2p with 1, 1, 1, 1, 1, and then a double filled. But right now, we're just going to worry about making sure we can see that there's 6 valence electrons. But it is more advanced, so AP chemistry. Okay, yeah.
Is this version like the more advanced version of how we would do like oxygen and have like the dots for like Mg and stuff? Like I learned this in 8th grade and we did this, but we didn't do it with like brackets and like plus 2 and like
It might be the more advanced. I might have to go back and see what you're talking about more in detail. Okay, but ions are very easy. They transfer electrons, they have a charge, boom, we're done. Okay, let's go ahead and move on to covalent. Those are the ones you're going to want more time with right now. Okay, so this is a good example of a diatomic. What's diatomic sound like it means? 2 atoms, right? This is a diatomic molecule called chlorine, and it's labeled generally Cl2. But here's the problem. This chlorine, that's the first one, has how many valence electrons? 7. The second one has 7 valence electrons. How electronegative is chlorine? Look on the periodic table. Where's it at? It's right there, right? How electronegative is it? Very electronegative. What does electronegative mean? So, say it in 2 words. Say it again? Okay, so attracts electrons. I'll say something similar to that. But it's attracting electrons in a bond. Okay, so that's why this is different, slightly different than our electron affinity. So both of them are like, I want electrons, and the other one's like, well, I want electrons too. So what's the compromise? They end up sharing these electrons. Not donating or taking, they share. So this electron here and this electron here come together to form a shared location. So it looks like chlorine on the left has octet, and it looks like chlorine on the right has octet. But truly, there's not 16 electrons here, right? How many are here? 14. It's just 2 of them are shared with each other. So in that case, that's a covalent bond because there's no charges, they're sharing, and it's generally because the electronegativities can't agree with each other. They're like, okay, you want it more than I do, you can have it, I'll be left without. Versus sodium. Look at sodium. How electronegative is it? I mean, not really. It's right over here on the left-hand side. It could care less about its electrons. But chlorine, was it chlorinated earlier? Yeah. Chlorine, again, is very electronegative. So that big, vast difference between those are like, okay, we're making an ionic bond here because I don't want electrons and you do. But this is very close electronegativity, so they actually have to share. So that's very easy to do. Let's do the same thing for HCl. What would I draw for H? Write this one down with me. H and what? What'd you say? 1 dot, 1 electron. It's in group 1. Okay, chlorine again. 7. Okay, those are 7 dots. And then I'll give you a chance to draw that as a covalent bond. Jillian, what you got? What do you say here? The H is what? So give me a favor.
Oh, covalent.
This is covalent. So backtrack. This is covalent, right? Non-metal, non-metal. So what would you say here? So hydrogen's not really going to have any more. It's just going to pop its right here in the middle, and then chlorine's going to be next to it, next to this bond, but chlorine still has its outside ones. So they're sharing these in the middle. It's just drawn together. No ions involved at all. It's drawn together. Okay, so you can imagine, like, you can have tons and tons of non-metals together. They can get a big party together and have a lot together. So let's look into this in more detail. I need to, we are talking about polar men. I'm going to ask for you guys to look at a paper on your desk first before I start moving on. There's a big chart that has a periodic table on it and a table beneath it. Do not take this paper. This is my master. I'll be putting the laminated so you understand that it's not for the home. Therefore, it's excellent class. Take a picture if you need to. Take a picture. But these little values on there actually they quantify the electronegativity values. So look at hydrogen and tell me the electronegativity of hydrogen. Shout it out. Look at hydrogen on the periodic table and tell me the electronegativity value. It's really hard to see, but it's there. I hear a 2.1. Can I get a second on that? Does everybody see 2.1? Okay. Look at oxygen. What's oxygen? 3.5. Okay, so what's the difference in those electronegativities? So 2.1 was hydrogen's, right? Is that right? And oxygen's was 3.5? What's the difference between those? When I say difference, I mean mathematical difference, which is subtraction, right? So 1.4 is the difference? Where does 1.4 fall in the categories that are listed in the middle of the paper right here? Where does it fall in these 3 categories? Not polar covalent, or ionic? Polar covalent. Polar covalent. So it's a covalent bond, right? So if I have electrons between hydrogen and oxygen in my example, they will form a covalent bond. But, Miles, what did polar mean again?
Opposite charge.
Right, so opposite, so unequal sharing of electrons. One side has more electrons than the other. So here's a couple of examples. Let's walk through that first, then we're going to draw some. So you guys have this chart. You will always have this chart for anything I need you to use it for, right? So do not memorize numbers. It's not worth it. What you're going to see, I'll just go to the next page. What you're going to see is that there are some electrons that are equally shared between two nonmetals, and some that are not equally shared between 2 nonmetals. So look at my 2 examples up here, and I've got chlorine and hydrogen in my examples. Or sorry, chlorine and hydrogen here, and hydrogen here. Which one looks like it's equally sharing electrons? Hydrogen, hydrogen. So would you call this one polar covalent or non-polar covalent? Non-polar covalent, because we have, and that's what N is here, non-polar covalent, because we have equal sharing. They're sharing equally, so neither side has a different charge. So I'm going to say no, I'm just going to say not polar. If we know that polar means opposite sides or opposite charges are difference in distribution of charge, then we should understand that this is equal sharing, meaning not polar. So I write down some helpful hints here for you. If you want to draw a picture as well, that's totally fine. And I'll give you some more information on how to determine that. What was the electronegativity value for hydrogen again? 2.1. The reason I'm saying this is I know from the numbers it makes sense. 2.1 for this hydrogen, 2.1 for this hydrogen. What's the difference? 0. That difference being 0 falls in that category on the chart that says 0 to 0.3 or 0.50. That does fall in the category of nonpolar covalent. Do the same thing, but you can definitely tell. You can definitely tell from this picture. Who's more greedy for electrons? Chlorine, absolutely. It's like, I'm hogging the electrons. I need these electrons, right? What is the electronegativity value for chlorine? Can you see it on your paper? What is it? 3 point what? 3.0? Okay, what's it for hydrogen? 2.1, what's that difference? 0.9. Where does 0.9 fall in our category? 0.9. Polar covalent, right? So this is polar covalent, and again, can you tell me which side of this bond, the chlorine side or the hydrogen side, which side has a partial positive charge? Which side would be considered partial positive, do you think? Hydrogen, because it has a lack of electrons, right? Electrons carry a negative charge. So if I'm carrying a negative charge, this side over here is partially negative. This side over here is partially positive. It's not a full-on positive or a full-on negative, because if we have that much going on, we have ions. And if we have ions, we have what kind of bonding? Ionic bonding. Not the case here, right? Two nonmetals. So it's just a continuum. And this little, like, lazy 8 here, can you see that okay? It looks like this. It's like, I almost want to do an 8, but I didn't quite. That's called partially negative and partially positive. That's just how you denote partially. It's a lowercase sigma. You'll see me write that a number of times. All right, so I want to see if you guys can determine if something's polar covalent or non-polar covalent. I have a couple examples for you on this page. All right, you guys do cesium with chlorine, oxygen with bromine. And I want you to tell me if it's polar covalent, non-polar covalent, or ionic. So you're going to do these values like we just did in class. So your process is you're finding the letters and you're writing down the numbers. So cesium, what's cesium's number? I don't have it in front of me, I'm trusting you. 0.7. What's fluorine's number? 3.0. What's the difference? 2.3. Okay, 2.3. Where does that fall in our category? Ionic. And guys, didn't you know that was ionic already? What is this? This is the metal, and this is a non-metal. So that doubly or triply confirms your belief. Metal non-metal is ionic. The little chart tells you it's ionic, and that's simply because they have a very, very, very large difference between their electronegativity values. So that is ionic. True. All right. Oxygen. What's oxygen's number? 3 point what? 5. And what's bromine's number? 2.8. What's that difference? 0.7. Where does 0.7 fall? Polar covalent. Okay, here's how we draw a polar covalent bond. Yeah. Metallic will not have any sharing at all in terms of its electrons. They won't have donations either. They throw them in a pool of electrons. They all float out together. We won't do anything like that right now. I'm saving metallic for another day because it's a totally different animal. Okay, so here's how you draw this. We draw a covalent bond, right? All we do is we draw a line between them. Woohoo! All right, line between them means 2 electrons. Okay, line means 2 electrons. Make sure you know that. But where are the electrons shifting towards? Towards bromine or towards oxygen? Who is more electronegative? How do you know that? Right, 3.5 electronegativity versus 2.8 electronegativity. The electrons shift themselves, just push a little bit forward towards the oxygen. So we draw an arrow pointing towards the oxygen. And then this little hash mark is just something that we have to do. That's how you draw a polar covalent bond. This little arrow system is called a dipole moment. It's a moment of dipole. It's a moment of polarity. One second. So the arrow points towards the partially negative side, and the little hash, doesn't that kind of look like a plus? Yeah? That's the partially what side? Partially positive side, because they have the electrons lesser time because they're not as electronegative. And I'll do this like about 3 more times to make sure you understand what that means. I had a question up here. Yeah. Because in order to share, so if we're going to share electrons, so both of us have octet, I have to put one in the pile, and you put one in the pile, and then we're sharing. Okay, so we both have to donate one to the bond. That's a good question. So the line equals 2 electrons because each donate 1 electron to the group for sharing purposes. Okay, I feel like we're ready to draw these a little bit more. Yeah.
When you find the difference, you just take the plus sum or minus.
Yeah, it's just absolute value difference. So we don't do anything negative. Okay, let's do a couple more examples. So I'm going to go to a couple pictures first, and then I'll come back to the rules. Here's what we're going to be working with. We're going to be working with larger molecules than just 2 together. For example, this first one has 4 elements together, or 4 atoms together. The way we always start is like this. And I have an acronym for you. We're going to be relating this to VSEPR, which is the VSEPR theory later. But if you can please write this down first, that would be very helpful. And I'm going to walk us through it as we go. V, count valence electrons. V. So I'm going to do one step at a time, and then I'll keep reflecting on the rules. But work with me as I go through the example as well. So we have about 10 minutes left. I thought we'd get farther. I'm coming up with a different game plan in my head as we speak, okay? So work with me. All right, so the first one. I have to take each of these elements and add up their valence electrons. So nitrogen. Find nitrogen on your periodic table. How many valence electrons? So if you stop writing the rules for a moment and work with me through this example. How many valence electrons does nitrogen have? What group is it in? It is in group 5. How many valence electrons does it have? 5. Okay, so nitrogen has 5 valence electrons. Plus 3 of hydrogens, but each of them have how many? Look at hydrogen. How many valence electrons does it have? 1. So I'm doing 3 hydrogens, so that's 3 times 1 valence electron. You got me so far? So nitrogen plus hydrogen plus hydrogen plus hydrogen. How many valence electrons is that? 8 valence electrons. Okay, so when I draw out a structure, I draw out a molecule, I can only show the valence electrons being shared. Because all those other electrons are on the inside, so the inner core electrons. They don't move, much less get shared, people, right? Never touch the inside, so that's why we're only counting valence. All right, check. We've done that. S means skeleton. Draw a skeletal structure of the molecule. You always put the single element as the center. And if there's numerous of the other ones, they go around it. Maximum you can put on is, well, I won't tell you maximum. You always want to attain octet. So I'm going to walk you through the first example, and then we're going to keep going. So nitrogen is my central atom. And I'm going to draw each of these others as appendages, as legs. So they get attached. And what do these lines mean? 2 electrons each, right? So hydrogen gets attached to nitrogen. Hydrogen gets attached to nitrogen. Hydrogen gets attached to nitrogen. So far I have a skeleton. And what was my rule for my skeleton? What goes in the middle? Say again? Why did I put nitrogen in the middle, not hydrogen? Okay, maybe because there's more valence electrons, but because it's the single one. So I have 1 nitrogen, but I have 3 hydrogens. Whenever you're drawing your skeleton, you always want to try to keep some symmetry. and that will help you always try to accommodate for the atoms present. Yeah.
Please go over what's the 5.
I'm going to go over that again in the second example. Yes.
What if there are more, what if there's not no more than just one? What if there's two nitrogen?
We're going to work through some more examples of that. So I want to answer questions, I think, with more examples. Okay? So we have now skeleton done. The next step is goals for all elements is to have octet, right? So let's go ahead and look how many electrons we have in our structure. Currently, nitrogen has around it 2, 4, 6, correct? Not octet. So what I need to do now is figure out where can I give it another pair of electrons. I can't draw them bonded like I have here. I don't have any more atoms. So what I do is I add a lone pair of electrons like this. 2 electrons, just like my Lewis dot models, but I'm drawing it as a lone pair because it's not attached to anything else. So now, nitrogen has 2, 4, 6, 8. Nice. It has 8 valence electrons around it. So I've added electrons. However, look at my hydrogens. How many electrons do they have around them? How many is this? 2. So this one has 2 valence electrons around it. This one has 2 valence electrons around it. This one has 2 valence electrons around it. Remember I told you the octet rule has some exceptions? Do you remember that? Okay, most things do accommodate octet. But look at hydrogen, guys. It's teeny tiny. It's only going to max out at helium's number. What's helium's number of electrons? 2. So the exception to the octet rule is the duet rule, which hydrogen has to follow. Hydrogen shall never, ever, ever have more than 2 electrons. It's just tiny. Okay, so hydrogen's happy, right? Nitrogen's happy. So we've gone through the electrons. And then sometimes you have to consider, do I need to make more pairs? Do I not? In this case, you don't. Everybody has octet. So as long as everybody's happy with octet or duet, we are good there. And then you review it by counting your number of valence electrons. How many valence electrons was I supposed to have in my structure? 8. How many do I have in my structure? 8. I'm good. VSEPR. All right, let's do another example, a bit more complex. I'm going to take the questions momentarily. Go ahead and tell me, how do we start with CCl4? I look at carbon and do what? I'm not ready for that yet. I haven't done my first step. Count how many valence electrons carbon has. Point to carbon on your periodic table. What group is it in? It is in the 4th group. So carbon has how many valence electrons? 4 valence electrons. Okay, I have 4 chlorines. So I'm adding 4 chlorines. How many? So this is 4, meaning 4 chlorines. How many valence electrons does chlorine have? 7, because it's in the 7th group. How many is that total? 32. Is everybody picking up what I'm putting down here? How am I counting valence electrons? I'm adding them by looking where? At the periodic table, looking for the group numbers. So the group number is the valence electron number of that particular atom. So then I did 1 carbon at 4 valence electrons because it's in the 4th group. 4 chlorines total give me 7 times 4, which is 28. 28 plus 4 is 32. All right, so counted my valence electrons, I have 32. How do I start my next step? So we're looking for a symmetry, right? So we're going to be trying to take 1 atom to put it in the center, which is carbon in this case. And I'm going to have, I see 4 chlorines, so I need to distribute them equally. So I'm going to just draw them kind of separated onto 4 corners. Chlorine, 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 and chlorine. So far, all I have is a skeleton. With that skeleton, though, I've accommodated how many electrons thus far? 8, because I have 2, 4, 6, 8. Who already has octet? Carbon already has octet. Do not add any more to carbon. But who does not have octet? All the chlorines don't, right? So I've gotten my V taking care of my valence electrons. My S is my skeleton. My E is to give everybody electrons up to octet unless there's exceptions. So how do I do that on all of these? Dots. So I have to pairs, right? So 2, 4, 6, 8. That's there. That's good. 2, 4, 6, 8. Good. 2, 4, 6, 8. That one's good. And then 2, 4, 6, 8. That one is good. So I just added a bunch of dots, but not just a bunch. Be specific. We added 6 dots to each of the chlorines. Yeah.
So why does the carbon and chlorine share?
Yes, we doubly count it. You're right. So carbon gets to count that as a shared bond, and chlorine also counts it as its own, making an octet. Yes.
I'm asking you that already. What if it was 5 chlorine?
So that's going to be something called expanded octets. So for example, and I want to come right back to that example because I'm not quite done yet, like this one, there are some things that can expand octet, meaning go over octet. You're going to see that when we do some examples tonight, okay? And you would add it as a 5th appendage, same to the central atom. You're really focusing on the central atom. Okay, so back here, double count. Let's go. Do I need to make any extra pairs? Nope, everybody's got octet. I reviewed it. How many electrons do I have on my structure? Can we count in 8s here? 8, right? 16, 24, 32. So that gets me all the way through the reflection process. Okay, so I'm going to challenge you guys a little bit and see what we can do with this. You guys have a picture of your sheet already, right? You have your electronegativity sheet picture. Do not take that with you. I need that in my next class. The paper I'm passing out to you is something I need you to start. You will not finish this, but I'm going to go ahead and have one example for you to do right now.
Just a quick announcement. The PSAT pre-admin will be today during second period and fourth in the cafeteria. Period 2, last name A through L. Period 4, last names again is M through Z. Please take attendance first before they come. Again, PSAT pre-admin will be today during second period. Second period, last names begin in A through L, report to the cafeteria. And fourth period, last names begin in M through Z. Band students with last names A through L come to fourth period pre-admin, not second period.
Okay. This table, guys, we are going to be working on until Friday. Listen for me so you know what's going to happen. Caroline, are you with me? All right, you guys are working on this until Friday. However, we're doing pieces of it every day. You are going to do the bond polarity section for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 of these. There are 12 structures, right? I want you to try that. All you're going to be doing, for example, CH3Cl, I need you to pick carbon to be your central atom. So when you're drawing your electron dot structures as well, you're going to be doing both of these columns because you can't really figure out the bond polarity until you figure out what it's connected to, right? Right? So, for example, carbon is going to be in the middle. Carbon loves to bond. If carbon is present, it is a central atom. Carbon goes in the middle. I'm drawing this for you right now. And there's 3 H's in a chlorine. So how many legs? 4 legs. 1, 2, 3, 4. It doesn't matter. You got 3 hydrogens, so I'm just going to put 3 hydrogens around it someplace. And I'm also going to be putting a chlorine around it someplace. But I'm just giving you a skeleton right now because at that point, I know what bonds are present. I have a carbon to hydrogen bond, yes? I look on my electronegativity sheet and I can look at carbon and hydrogen. And I can do that over here. I have a carbon-hydrogen bond. Same thing for carbon and chlorine. Try for me. Try and I'll answer questions on this tomorrow, okay? Or during teal if you're coming to my teal. Have a great day. Ask me questions. Ask me questions.
Let's go, Misha.
Oh. Yeah, I'm gonna pause this in your repository.
For student advisory board thing, would you think that they